If you enjoyed this video, don't forget to like, comment, and subscribe. Imagine a place on our own planet more alien than the surface of the moon. It is a realm of absolute darkness where the sun has never shone. This is the Mariana Trench, a deep scar in the Earth's crust in the western Pacific Ocean. Picture the Grand Canyon, a truly vast chasm in its own right. Now stack 7 of them, one on top of the other, and you still would not reach the bottom of this trench. Its deepest point, a spot known as the Challenger Deep, plunges nearly 11,000 meters, almost 7 miles, below the waves. If you were to drop Mount Everest into this abyss, its majestic peak would still be submerged with more than a mile of water pressing down upon it. This is not just a deep hole, it is another world. The journey downward is a descent into the unknown. The familiar sunlit waters of the surface teeming with vibrant coral familiar fish quickly fade. First, the warm blues give way to a perpetual twilight, where only the faintest glimmers of sunlight penetrate. Then, even that disappears, and you are enveloped in a cold, inky blackness that is absolute and unending. The temperature plummets to just above freezing, a stark and hostile environment where warmth is a distant memory. Down here, the silence is profound, broken only by the hum of a submersible or the faint, ghostly sounds of life forms we are only just beginning to understand. It is a place of extremes, a silent, dark, and frigid kingdom that holds some of Earth's greatest secrets within its depths. To understand the challenge of living in the Mariana Trench, we must first grapple with the concept of pressure. On the surface, we barely notice the weight of the air around us. We are perfectly adapted to it. But imagine the weight of a single jumbo jet, a Boeing 747, resting on your shoulders. Now imagine a stack of not 1, not 2, but 50 of these massive airplanes, all pressing down on you. This begins to approach the immense, relentless pressure at the bottom of the trench. It is a force so powerful that it can compress solid objects and warp steel, a force that seems utterly incompatible with the fragile machinery of life. This is the pressure paradox. How can anything, let alone a living creature, withstand such a colossal weight? Think about the everyday stress we feel. Deadlines, the responsibilities, the constant demands. We talk about feeling under pressure, but that's a metaphor. In the deep sea, the pressure is literal, physical, and 1,000 times more intense than anything we can imagine. It is 1 ton per square centimeter over 16,000 pounds per square inch, equivalent to balancing the entire weight of the Eiffel Tower on the tip of your finger, a number so large it almost loses meaning. Yet for deep inhabitants it's simply the air they breathe. The immense force exerted by the column of water above is known as hydrostatic pressure. It is a simple concept. Water has weight. The more water you have on top of you, the greater the weight. For every 10 meters you descend into the ocean, the pressure increases by 1 atmosphere. By the time you reach the 11,000-meter Challenger Deep, you feel roughly 1,100 times the pressure. This pressure is not directional. It does not just push down from above. It pushes inward from all sides equally and relentlessly, squeezing everything with an invisible, powerful hand. For life as we know it on the surface, this squeezing is catastrophic. Our cells are intricate machines. Their components, especially proteins, need very specific 3-dimensional shapes to function. Proteins act as enzymes. Proteins act as structural supports. Proteins act as messengers. Imagine a key that needs a precise shape to fit a lock. Hydrostatic pressure acts like a vice, warping that key until it is useless. It can force water molecules into tiny crevices of a protein, disrupting delicate folds and rendering it inactive. This process, protein denaturation, is what happens when you cook an egg. The clear egg white turns solid and opaque as its proteins are permanently altered. Extreme pressure can have a similar disastrous effect. Furthermore, the very membranes that enclose our cells would fail. Under immense deep pressure, these lipid membranes would be compressed and lose fluidity, becoming stiff, almost like wax. This would shut down the cell's ability to transport nutrients in and waste out. The creatures of the deep did not evolve to resist the pressure. They evolved to incorporate it into their very being. Their primary strategy is simple yet profound. They have largely eliminated the air-filled cavities that are so vulnerable to compression. Unlike surface fish that use a swim bladder to control buoyancy, deep-sea fish have no such organ. Their bodies are mostly water and tissue, which are far less compressible than air. By being almost entirely solid and fluid, they achieve a state of equilibrium with their surroundings. The true genius of their adaptation, however, lies at the molecular level. Deep-sea organisms have evolved special proteins that are fundamentally different from our own. These proteins have a more stable, resilient structure, often with a tightly packed core that resists being squeezed out of shape. More importantly, these creatures produce small organic molecules called piezolites, a name derived from the Greek word piezen, meaning to press. The most famous of these is trimethylamine N-oxide, or TMAO. This remarkable compound works by supporting the proteins, helping them maintain their correct functional shape and counteracting the distorting effects of the immense pressure. Among the most iconic residents of this deep dark world is the Mariana snailfish, Pseudoliparus suirae. This small, translucent, tadpole-like fish, it holds the record for the deepest living fish ever found, thriving at depths of over 8,000 meters. It looks fragile, almost ghostly, with its pinkish-white skin and lack of scales. You could be forgiven for thinking a gentle breeze might damage it, yet this delicate-looking creature is one of the most pressure-adapted vertebrates on the planet. If you enjoyed this video, don't forget to like, comment, and subscribe. Venturing deeper, we encounter creatures that seem to have sprung from the pages of science fiction. The giant amphipod, Alicella gigantea, is a crustacean that resembles a colossal woodlouse. It can grow up to 30 centimeters long, more than 10 times the size of its shallow water relatives. These pale giants are scavengers, congregating on any food that happens to fall from the waters above: dead fish, whale carcasses. Another bizarre inhabitant is the xenophyophore, a single-celled organism that can grow to the size of a fist. These are among the largest individual cells known to science. They construct intricate, branching shells, called tests, from sediment and minerals found on the seafloor. From a distance, they might look like strange, flat sponges or pieces of coral, but they are in fact giant amoebas. We also find the eerie anglerfish, a classic icon of the deep. While most species live in the slightly shallower midnight zone, their adaptations are the stuff of legend. The female dangles a bioluminescent lure from her head, a living fishing rod that glows in the dark to attract unsuspecting prey. In this world of perpetual night, creating your own light is a powerful advantage. Many anglerfish species also exhibit an extreme form of sexual parasitism. The tiny male fuses his body to the much larger female. The discovery of a thriving ecosystem in the Mariana Trench has fundamentally altered our understanding of biology. For a long time we defined life by the conditions we experience on the surface: moderate temperatures, abundant sunlight, low pressure. The deep sea has shattered these limitations. It has shown us that life can exist and even flourish in environments we once considered sterile and uninhabitable. The creatures of the abyss are not just curiosities, they are living proof that the habitable zone is far broader and more varied than we ever imagined. They force us to reconsider the most basic requirements for life to take hold and evolve. This revelation has profound implications for the search for life beyond Earth, a field known as astrobiology. When we look for life on other planets and moons, we have historically focused on worlds that resemble our own. Those with liquid water on their surfaces and atmospheres that could support Earth-like life. But the Mariana Trench provides a powerful analog for other, more extreme environments in our solar system. Jupiter's Europa, Saturn's Enceladus are thought to harbor vast liquid water oceans hidden beneath thick shells of ice. Dark cold under immense pressure, conditions remarkably similar to those found in Earth's deep-sea trenches. Our journey into the deep is far from over in many ways. It has just begun. We have mapped the surface of Mars with greater detail than our own seafloor. The Mariana Trench remains one of the least explored places on Earth. Each new mission, each dive with a submersible brings back new species, new data, new questions. Leading the charge? ROVs, AUVs. These robotic explorers can reach depths and durations impossible for humans. High-definition cameras, powerful lights, robotic arms for sampling scientific sensors, they become our eyes, hands, and laboratories in the deep. Future AUVs will use artificial intelligence, decide on their own, identify targets of interest, carry out complex missions without constant supervision. They will create detailed 3D maps of the seafloor and monitor ecosystem changes over time. Another frontier, deep-sea landers. As our technological ability to reach and explore the deep sea grows, so too does our responsibility to protect it. For a long time, the abyss was considered too remote and too vast to be harmed by human activities. We used the deep ocean as a convenient dumping ground, assuming that our waste would simply disappear into the immense darkness. We now know that this is a dangerous misconception. The deep-sea ecosystems of the Mariana Trench and beyond are not isolated. They are connected to the global ocean system, and they are surprisingly fragile. The slow pace of life and cold temperatures mean that these environments recover from damage far more slowly than their shallow water counterparts. Plastic pollution, once thought to be a surface problem, has been found even in the deepest parts of the Mariana Trench. Microplastics have been discovered in the guts of amphipods living at nearly 11,000 meters, a sobering testament to the pervasive reach of our waste. We are also seeing the looming threat of deep-sea mining. The abyssal plains are rich in valuable minerals like manganese, cobalt, and nickel, metals that are in high demand for batteries and other modern technologies. The Mariana Trench is more than just a geographical feature. It is a symbol of the vast and profound mystery that still lies at the heart of our own planet. In an age where we have sent rovers to Mars and peered into the dawn of the universe with powerful telescopes, it is humbling to remember that over 80% of our ocean remains unexplored, unobserved, unmapped. These dark, silent depths hold answers to some of the most fundamental questions we can ask. What are the ultimate limits of life? How does evolution work under the most extreme pressures imaginable? And what other strange and wonderful life forms are waiting to be discovered? Our journey into the abyss has taught us to be humble and to expect the unexpected. The snailfish swimming peacefully in the crushing pressure of the Challenger Deep is a powerful messenger, telling us that the rulebook for life is far more flexible than we ever knew. This calls for a renewed sense of curiosity and a global commitment to ocean exploration. So the next time you look out at the vast, blue expanse of the ocean, remember the world that lies beneath. The abyss is not empty, it is full of wonder. And we have only just begun to scratch the surface of its brilliant, uncharted soul. If you enjoyed this video, don't forget to like, comment, and subscribe.